Hello everyone, my name is James Church. I am a graduate student in Mississippi, and I have a new part-time job, and so my new part-time job is professor at a different college, and so that's just a little bit of background behind me. I teach a lot of the introductory courses, and well, I teach courses at all levels, but primarily they stick me at the introductory level. So that's why I focus on introductory languages, Java, C, C++, Python. And a lot of times I'm writing algorithms for the students, and I have to show the correctness of those algorithms. So mathematically, the mathematical basis for those algorithms. So I am more focused on the mathematics behind this talk, but we will focus also on the cryptography. Math is hard, let's go shopping. All right, so where I would like to start is the reason why we need our encryption schemes. Now, there's a really bit of recent news, probably a lot of you already know this. This was a New York Times article. The author was Charlie Savage, September 27th, 2010. What was the title of that article? I've got it up here. U.S. tries to make it easier to wiretap the internet. So the Obama administration is trying to propose legislation that would require U.S. companies to, in the event of a subpoena to say something has happened, they need to get information. A lot of these services, such as Skype, are encrypting this information so that not even Skype can tell you what is passing over their networks. The U.S. is trying to pass laws saying that, oh no, in the event of some extreme circumstances, we need to pull this out. And a lot of groups like the ACLU are saying this is an invasion of privacy. Just to give you a quote from the article, no one should be promising their customers that they will thumb their nose at this U.S. court order that they're proposing. They can promise strong encryption, they just need to figure out how to provide us, meaning the government, in plain text. So they are not worried about the technology aspects, they just want to know how quickly they can get their plain text information. So as an aside to this talk, so now you know the importance of it, what I would like to focus on is the mathematics behind this cryptography, because hey, we may enter an era where we need to rely more upon ourselves than other companies' encryption schemes for our own privacy needs. So you can do anything with math, almost. Wait, what can I not do with math? I can't get a date, and I can't divide by 0. Well, maybe I can divide by 0. All right, but I have special powers. Anyway, so to make an encryption scheme, you need an imagination, and to break the same encryption scheme, you are going to need the same imagination as the encryption scheme maker. Of course, this is how it's always been for classical encryption schemes, the Caesar cipher, the veneer cipher, and such as that. As soon as you figure out how the person making the encryption scheme manipulated the data, you perform the reverse, and you have the original plain text. Now with mathematics, we are making this much harder, and we're going to start looking deeper into that. Oh, and I do have lots of algorithms in this talk, but if you aren't interested in the algorithms, I also have lots of pictures of cute animals. So there you go. Enjoy that. So let's look at the 3 different areas of cryptography. I'm going to focus on one and exclude the other 2. Primarily, we're going to look at this asymmetric. So but first, we're going to focus on classical cryptography. So with classical cryptography, these are our old schemes: veneer cipher, ROT13, Enigma cipher, World War II. The secret decoder rings, and ADVGX product cipher. A lot of these were simply replacement schemes that people came up with. And a lot of these have a great place in history. I threw ROT13 in there. ROT13 is, well, I'm sure most of you know what ROT13 is. You take a letter of the alphabet, you add 13 to it, and you get a new letter of the alphabet. And because there's only 26 letters of the alphabet, if you do it twice, you go back to the original letter. Very weak scheme. Most people can pick out what it is immediately. So because they aren't as heavy on the mathematics, I'm not going to really spend a whole lot of time on discussing these classic schemes because they're all just wildly different. So let's go over to symmetric cryptography. This is also known as private key cryptography. A little more sophisticated than your classical schemes. In these schemes, you have a private key. So you have a function that requires two inputs. You have your plaintext message and the key, and outputs the encrypted text. And in order to take your encrypted text and bring it back to your original, you have to have the encrypted text. You use the exact same function and that same private key. So this bit of text, you might think of it as a passphrase or a passcode. This is so symmetric cryptography. In other words, you use the same function and key to both encrypt and decrypt your message. That's hence the symmetric. This is great if you have a lot of personal documents and you wish to encrypt your own documents and you're the only person who's going to know the key. Is a little more problematic if you want to go into, if you have two people who wish to exchange an encrypted message. So two people, they agree upon a private key, and then they're separated, and then they have to transport the key. Hopefully, they have some backup plan as if that key ever gets out into the wild, because then if the key ever gets out into the wild, well, any cipher built on that key is automatically compromised. So examples of symmetric key encryption, we've got the XOR cipher, AES, two-fish, blowfish. Again, some of these are very sophisticated, such as blowfish, and you can use them for your personal work. Because of the mathematics behind this, I do like to talk about the XOR cipher, even though I wasn't going to talk about this for the whole talk. Just briefly, the XOR cipher, if you've ever taken a philosophy of logic class or an introductory programming course or an introductory electrical engineering course, you may be familiar with the exclusive OR, which you have two Boolean inputs. A Boolean is either a true or a false. And if one is true and the other is false, then your result is true. And if both are false or if both are true, then the result is false. And so we can do a simple example here. We have a private message, X, and we have a secret key, A. And so our function is we're going to XOR X and A. So let's encrypt the message. And with our XOR, you got to convert those two letters to binary code. So 0100, 0101100, and then the A is 01000001. If you perform the exclusive OR of X and A, you get a binary sequence that. It doesn't make any sense to me, it doesn't make any sense to you, it doesn't make any sense to the person out in the field if they don't know our secret key. In the Diffie-Hellman paper, or is it Diffie-Hellman paper, he makes the quote, cryptography is the art of making information useful for your friends and useless to your enemies. So there we go. That's an example of a useless message, that sequence of binary. To decrypt it, we simply take our private key and our encrypted message, and we perform the XOR again. Again, same function, same symmetric cipher key, and if you produce that result, you get your X back. And if your key is equally as long as the message you're trying to encrypt, that is known as a one-pad cipher, or one-time pad cipher. So, and mathematically it's been shown that one-time pad ciphers are impossible to crack. So symmetric key ciphers are suffer from the key distribution problem. You can use frequency analysis and take digraphs where you have sequence of letters. You can pair the letters up, and if you, so in frequency in our English language, if you know the language that the cipher is going to be in, if you know it's going to be English, then you can study the English language, and you know that TH, HE, IN, ER, AN, and RE are the most frequent pairings of letters in our vocabulary. And if you study the enciphered code, you can see that pairings will slowly float up to the top. And you just take the top pairing, and that's probably going to be TH. And that gets you that much closer to breaking the encryption. All right. That's pretty much it. Oh, yeah. More cute animals. I said I was going to throw cute animals in there, so there you go. We're going to, yeah, great. So let's go to asymmetric cryptography. This was the form of cryptography proposed by Diffie-Hellman. This was in, I've got it here, 1976, public key encryption. You have, instead of one key that both people know about and you hope never leaks out into the wild, you have a public key and a private key. The public key is public, everyone is allowed to look at it, and the private key, only you know about it, and you do your best to share it with no one. So we've got Alice and Bob here as my little ugly stick figures. Bob would like to share a message with Alice, and so the very first thing Bob does is he retrieves Alice's public key. By the way, Alice has made this public on, say, a website. So Alice encrypts the message using the public key, and the only person who can decrypt that message is Alice with the private key. The fascinating thing about public key encryption is that now anyone can send a message to Alice, and only Alice can read it. But Alice has no way of knowing if Bob, the person who she's waiting on a message from, is actually Bob. She could get lots of messages, and the messages could be confusing. So there's an advantage to public key cryptography where we can make the process more complicated, where Bob can encrypt a message using his own private key, which means it can only be decrypted using his public key. So Bob encrypts a message again using Alice's public key. The message is transferred. It's been encrypted twice. Now Alice has it. Alice decrypts using the private key. Alice decrypts using Bob's public key. Because of this double encryption scheme, now Alice knows that Bob that this is definitely Bob's message. This is probably going to be my busiest slide in the presentation. All right. But what I really want to talk about is RSA encryption. So here's where the direction of my talk changes. We're going to be talking about RSA encryption. Rivas, Shamir, Alderman. This was an encryption scheme made in 1978, immediately 2 years after Diffie-Hellman's public key advancement. So we have I want to say it was the first, so I've got a disclaimer there, it's an early scheme. Anyway, this scheme is based on very large prime numbers. So we're going to be focusing more on the prime number aspect of RSA. So here's an example of a prime number. And so there it is, it just begins. Okay, this is a 1,000-digit long prime number. It is a very large one. It is not the largest. I went to a prime number database website. By the way, the finest prime number database website is primes.utm.edu, my alma mater. Before we go deeper, we need to discuss how prime numbers are generated. Oh, and I went down to the very bottom of the list with the smallest prime numbers and pulled that one. So there we go. There are prime numbers much, much larger than this one. So how can we quickly determine a prime number? Because that is the foundation of RSA. We need a little math. All right. So we have a basic concept from your 4th grade math class called modulus, or remainder. So we have two numbers and we wish to divide them. 7 divided by 4 is 1.75. We don't have to say 1.75. We can just pick a different representation of that. 7 divided by 4 is 1 remainder 3. Well, we don't care about the 1. I got the 1 remainder, 1R3, 1 remainder 3. We don't care about the 1. We just care about the 3. So 7 mod 4 is 3. So whenever I talk about modulus, I'm talking about computing a division and getting the remainder. That is our mod. Whoop. There we go. I hit the button. So we have prime numbers. Prime numbers are numbers with no factors. So there does not exist a number from 2 to n minus 1, where n is a very large number, or just any positive integer, where you can't find a number where n mod that number equals 0. So prime numbers with no factors except 1 in that number, so prime numbers are numbers with no factors except 1 in that number. All right. In other words, so we have a number n. We can loop from 2, the number 2, to n minus 1 and compute the mod. So I've got the percent sign is mod in Python. So there is the Python algorithm there. Def is prime. So we start at 2, f equals 2. We're going to loop. And if that ever equals 0, we return a false. And if it ever gets to the end, we're going to return true. We have a prime number. Yay, we have the most basic prime number detection algorithm. This algorithm sucks. One of the prime reasons why this algorithm is awful is because once you compute 2, you no longer have to compute even numbers. So when I showed you that 1,000-digit long prime number, you take that number, you divide by 2, and that's how many even numbers are between 2 and n minus that large prime number minus 1. That's how many wasted calculations you have in your algorithm. All right, so this is worthless. We need a better approach to finding prime numbers. So rather than saying that a number is prime, why don't we just say it's probably prime? So this is an approach to a randomized detection on prime numbers. So we could just pull random numbers out of the air between 2 and n minus 1, and if they ever randomly hit on a mod 0, we know it's not prime. And if all of our numbers check out, then we know it's probably prime. All right, so we test repeatedly. Now, how much should you test? And I would recommend probably a log-based value of the large number. But still, this algorithm has its own problems. For instance, if we pick any of the small prime numbers, we're still replicating wasted cycles in our algorithm. So to pick bad choices of f, such as 2, 3, 5, 7, these are really small prime numbers. These numbers multiples of these numbers recur repeatedly in very large numbers. This is still a wasted version of the prime numbers. We're going to need more. So let's start off with the greatest common divisor. All right, so we've been talking about factoring numbers, and prime numbers have no factors. So here is the greatest common divisor. So let's take two numbers, 28 and 35. So I've got all divisors of 28 and 35 listed there. And the largest number that is common in both those sets is the number 7. So the greatest common divisor is 7. So Euclid, very old mathematician, BC era, he came up with this algorithm for determining greatest common divisors. For small pairs of numbers, this actually works. You didn't know Euclid was a Python programmer, did you? Even though he existed 600 BC. So there's, say what? He must have. So there is the prime number algorithm. As you can see there, we have two inputs to the algorithm, A and B. And while one of those algorithms is not 0, we are flipping the numbers back and forth. We're juggling the numbers. And as soon as B reaches 0, that A turns into our greatest common divisor. Very handy algorithm to have when searching for coprimes. Now, there we go. I've got a message at the bottom. If the GCD of two numbers is equal to 1, we call these numbers coprime, which means you can think of GCD as a similarity score. That's in machine learning. There's the concept of similarity scores. This is probably not the most appropriate application of that term, but you can think of them as a higher GCD means that there's a higher similarity between these two numbers, loosely. So a GCD of 1 is going to have, you know that these two numbers are fairly different. All right, more math. We need to talk about what's known as the modular multiplicative inverse. So you have two numbers, A and B, and you've got to make sure that they're coprime. Coprime, again, greatest common divisor is equal to 1. the modular multiplicative inverse satisfies this equation here. A times a number, x, we don't know what x is, mod b is equal to 1. So we have, I've got an example over here, 5 and 7. 5 and 7 are relatively small prime numbers. We've got to come up with a modular multiplicative inverse. This is important for the RSA encryption, by the way. So 5 times a number, mod 7, has to be 1. There are infinitely many solutions to this, which is why you can't just come up with a definitive math formula to solve it. You pretty much have to rely on computers to do it. 5 times 3 mod 7 is 1. 5 times 10 mod 7 is 1. You always pick the smallest one. So the best answer is 3. For these two numbers, we compute 3. All right, so we discussed coprime, greatest common divisor, modular multiplicative inverse, and now we get into a third algorithm for detecting prime numbers. And this is known as Fermat's little theorem. So Fermat was a mathematician in the 1600s. This is an algorithm that he came up with in 1640. And so because it's Fermat's little theorem, not to be confused with Fermat's last theorem. Fermat's last theorem was turned into a book by Simon Singh called Fermat's Enigma. Great book, won National Book Award. Encourage you to read it. This is a different theorem that he wrote. The reason why it's called Fermat's little theorem is because the proof is really short. So you have a prime number, p, and you have a number x, which is coprime to p. Oh, and because it's small, we're going to zoom in here. So you have p is prime and you have x is coprime. Fermat figured out that x to the power of p minus 1 mod p is always equal to 1. Always equal to 1. If you have a prime number, x, the power of your prime number, minus 1 mod p, you're at 1. This comes in handy. We can build a new randomized prime number detection algorithm based on that formula. So here we go, randomized algorithms, part 2. We're going to say p is a number that we don't know if it's prime or not. And we're going to say x is any number from 2 to p minus 1. Now I said in the last slide that x and p have to be coprime. Okay, we're going to ignore that. If you've already forgotten what greatest common divisor is and coprime, throw it out the window. We're not worried about that now. So for testing prime numbers, we have the Fermat prime testing algorithm. Here I've got an algorithm where I'm inputting a number p, and I've got k is equal to 50. You see that line there? That just means I'm testing the algorithm 50 times. So I'm picking out a random number, and I'm passing it through Fermat's last theorem. You can see that line. X to the power of p minus 1 mod p is not equal to 1. We know it's not prime. We're going to loop. And if it ever reaches the bottom of the algorithm, it's going to say possibly prime. Okay, there's still problems with this algorithm. Math is hard. Still problems. So in 1899, remember Fermat's little theorem was in 1640. In 1899, a mathematician theorized that there were probably not prime numbers that fit Fermat's little theorem. But it wasn't until 1910, a mathematician by the name of Carmichael came up with Carmichael numbers. And these are not prime numbers that still fit all of the rules of Fermi's little theorem. All right, so for example, you've got a number 561. 561 is the smallest Carmichael number. The reason why it's called a Carmichael number is because it fits all the rules of Fermat's little theorem, and it's still not prime. So that algorithm which I just showed you, this number would still say, yeah, it's probably prime. It's not. How RSA key generation works. We now have enough math in order to actually start talking about RSA key generation, which is the basis of the whole RSA encryption scheme. So I never thought I'd get here either. You're probably sitting there going, hey, hurry it up. All right, so we pick out two really big prime numbers. And in fact, the original prime paper on the topic said, pick out numbers with at least 100 digits. And at this point, our computing power has gotten sophisticated enough, I'd say, hey, go 200 digits. You compute in, and that's step 2, compute in, which is simply your two giant prime numbers multiplied together. We compute totient n. I didn't discuss Euler's formula, which is an improvement on Fermat's last theorem, but still a little more math. If you're more interested, look up Euler's formula, or Euler's totient function. But in this case, it's really easy. You take your two prime numbers, you subtract one from both of them, and you multiply them together again. You pick out a prime number e, and this can just be any number you want between 1 and your p times q value, which we've already called n. In fact, I've read papers that just say, pick out the number 65,537, which is just a good prime number. And now we compute d, which is the modular multiplicative inverse of e and totient n. So you have e and totient n. You compute the modular multiplicative inverse. Again, you saw that from a couple of slides ago. And now we have all of the variables we need in order to create our public and private keys. Your public keys are going to be values n and e, and your private key is going to be letters d. Now, as we've already discussed, if you have that variable n, you've got n right there. With that number n, you can step backwards and recreate all of those steps. And by the way, that's public. So my question was, when I first heard about this, why can't I just factor in? Because if I can just factor in, I have the whole scheme and I have your code. And here's the deal. Well, factoring numbers is quite difficult. So why is this so secure? You could potentially reconstruct all the variables, but this is difficult. So the RSA, the three authors who wrote the paper, have turned their encryption scheme into a company, and they've published 55 numbers that are called semi-primes. Semi-prime numbers are simply, you take two prime numbers and you multiply them together. That's a semi-prime. So this is semi-prime RSA 768, and you'll see it's got 4 lines devoted to just one really long number there. That is a semi-prime and is the multiplication of those two really long numbers below that. The number was published in spring of 2007. A team of 10 researchers with 80 computers poured through it with lots of detection algorithms. And finally, it took them 2 years of number crunching to come up with those two bottom numbers. This is the largest semi-prime that's ever been cracked. If you take those two prime numbers right there and simply multiply them together, it takes about a half second to get that top number. To give you so it takes 2 years, 80 computers, hundreds of thousands of computing hours to go from step 1 to step 2. It takes a half a second to go from step 2 to step 1. This is the security behind RSA. And so, yeah, well, all right, so now we have the upper mathematical bound of why RSA works. So just the fact that the number is out there and you could potentially factor it doesn't mean that you have the resources to factor it. So I was trying to think about how I would break RSA encryption now that we have an idea. We could factor in, which I've already discussed is probably practically infeasible. We could social engineer it, steal. Or we could create storage tables of semi-primes, much like MD5 and SHA-1 has done. So I'm sure you're familiar with MD5 and SHA-1. These are hash keys, and large hash databases exist on the internet to, excuse me? Rainbow tables, that's right. I'm proposing rainbow tables of prime numbers. And to my knowledge, there is no database of rainbow tables of semi-primes. So here we go. If someone ever wants to start this project, we could get this off and running in order to break RSA. I promised Cordon that I was going to talk about the fast Fourier transform in cryptography. In fact, that was really what I wanted to be the whole basis of my talk on, which is the FFT, because I really like the fast Fourier transform algorithm, which is a tool from signal processing. Signal processing and cryptography don't really have a whole lot of overlap other than maybe frequency analysis. But one, you're dealing with a digital signal that you know is not encrypted, the other one you know is encrypted. So the fast Fourier transform is a tool for looking at data sets. You have a time, imagine a song, and that song has, if you look at the waveform of that song, it's going to be peaks and troughs. And the fast Fourier transform converts that into a frequency domain. So you see all of the high signals and low signals in one convenient graph. Let's see here, I've got it down here, where was it? 1968, mathematician Strassen figured out that you could use the fast Fourier transform for multiplying large numbers quickly. I've already said that takes about a half second to multiply large numbers just inefficiently. We can do it even faster with sophisticated algorithms, such as with the Strassen FFT algorithm. And I figured this is probably a great point to mention that we could start building our large table of databases. All right. This is where I just say, I'm done. There are more algorithms for detecting prime numbers, and the two algorithms for detecting prime numbers that I am most interested in are called Rabin-Miller and the Jacobi algorithm. I have implemented Rabin-Miller in Python. I can show you the code for that and some of the more mathematical basis behind that, but I figure we'll keep it at just factoring and Fermat's little theorem. All right. So there we go. All right. Do you have any questions?